Okay, so hello everyone. Welcome back after the break. There will be a few more talks now. So one of them will be gaining insight from imaging data presented by Katja Buehler. She's the scientific director of the VIA-WIS, or in German Zentrum für Virtual Reality und Visualisierungsforschung in Vienna, which is a very long name, I think the longest so far. And she's the scientific director of this institute, which actually one of the purposes is to really bridge the gap between the industry and academia. Yes, and she's also leading a group there about biomedical image analysis. And today she will not just talk about gaining insight from data, but also how to do that in a reliable and trustable way. So I'll now pass on to her.
Yeah, thank you for this introduction and the possibility for me to speak here. I'm really fascinated by all the talks I heard already. So I will talk about insight from imaging data, and that's a big topic actually. And I discussed with Thomas that I will focus on reliability because this is a very important topic and something where we go into with our research quite a lot because we cooperate with big companies in the medical field and in pharma industry, but also in manufacturing. So it's not all about biology, but yeah, you will see. I don't care as a computer scientist what is on the image, actually. It's all the same. But I'm fascinated by imaging data, and biomedical imaging data is so rich in information. So you see all across the scales from a molecule we heard about just in the previous talks up to satellite imaging data. And at VIA-WIS, we even have more data. We have also data from whole planets, from the Mars. We are working together with NASA, so it's another scale. It's from the orbit of the Mars down to the surface of the Mars. But I'm in the biomedical field mainly. And if we look at the challenges which are connected to imaging data, so imaging data is really rich in information. So we have a very dense information space. If you have an image can show me the body of a person, and it tells me from diseases about physiological status, up to changes in the body. We have a high variability in imaging data. Even if I just look at one single modality, depending on the acquisition process, it can be highly variable. This is the acquisition dimension, and on the other hand, also the subjects I'm investigating in, they also are highly variable. And we heard this also yesterday. Yeah, so humans are very diverse, for instance, plants, everything. Then another challenge is the data integration. If we see here the scales, so correlated multimodal imaging is a big topic in Austria. There's an Austrian bioimaging node which is focusing on this, and actually the data integration across the different modalities and from really nano to macro is it's one of the biggest challenges at the moment. And then the data size itself, if we are talking about deep learning, we have to think about that if you have a 3D image, it's very dense in data. It's big data compared to text data, for instance. And if I want to learn on these data, I need a lot of computational resources. So I have to be very efficient in what I do. So in my group, we are following a holistic approach to insight from data. What does that mean? On one hand, we are working on image analytics topics, image enhancement, semantic enhancement of data, annotation of data, classification of data. Another important part, if you want to gain insight, is the visualization of the data. You think, okay, a photo or a single slide is easy to visualize, but if it comes to 3D data, it's already getting more complicated. And then if I have semantic annotations, I probably also want to visualize these, and I want to interact with the data. In the next step, if I have these data, I also want to quantify it. I want to mine it. So I have to organize the data. I have to organize the quantities. I have to visualize this and visualize them, and I have to make them, for instance, mineable. And we have another project. I will not talk about this, but we are working with pharma industry where we are integrating big amounts of spatial data for neuroscientists to find targets, pharmacological targets. Yeah, and at the end, if you have all the data analytics and visualization and quantities we extracted from the imaging data, I can do finally also some machine learning on this in addition to derive further insights from my data. So altogether, where is AI? Everywhere is AI in this process. And I will mainly concentrate on the first part now, on the image analytics part. And if we go through this, so what are the benefits to integrate here AI? I think this is on one hand, the large scale data processing and analytics capabilities. If I automate things, that's very clear, but also it's an acceleration of workflows. It's acceleration of the insight process because time is money in the medical field, in the industrial field, everywhere. So it's about cost reduction, and it's also about customer satisfaction. If you can improve visualization and data insight and diagnostic processes for radiologists or scientists, this is very important. And as we are working with industry, we have to take a lot of care to have a technical feasibility. So stuff we do has to be very efficient. It has to have high performance, and it has to be reliable, transparent. It has to keep human oversight because we have upcoming regulations, and we also have to consider always legal and ethical constraints. So yeah, the relevance of which of these requirements are really necessary depend on the application area and also on the, let's say, risk level of applications we are developing. If we are having if we are working directly on diagnostic processes, we are in the highest risk level, actually. Yeah, so what I heard here very often, isn't it solved? We have all these big, shiny, large models now. We have ChatGPT, we have multimodal models combining ChatGPT with other transformer-based models. We have a model which is called Segment Anything, SAM, which was released by Meta recently, and also Monai, which is focused on medical data. Or CellPose, which is concentrating on cell segmentation. Yeah, they are there, but if we experimented a lot with them, they do not solve our problems. They provide a basis, which is there, but we have that problem that we have downstream problems with transparency. We have to refine these models, but even this is a very tidy process. If we have transparency issues, so we cannot use these models because we partially do not know on which data they have been trained. So there is a compliance problem with upcoming regulations, and they are very heavyweight, most of them. And this is a problem for us. Where we have stable solutions, these are like closed world problems, where I say I have a very strict imaging protocol, I have a very narrow space and variability, and there, in fact, we have solutions which are already quite performant, and we saw like 2 talks before one of such examples. So pathology actually is already a field where AI is starting to establish as a tool. So applying AI to biomedical imaging data. So we have here high demands on reliability, transparency, and performance, at least what we hear from our industrial partners. So we have the upcoming AI regulations, and there's also a switch from a more AI in the loop or human in the loop, which means, okay, the AI is using the human to annotate data towards a machine in the loop where we are using the machine to solve our problems. And the related challenges also here in realizing this is that we have, especially in the biomedical field, a lot of uncertainty in data acquisition, observed phenomenon, often a lack of enough annotated data. And in principle, there's still the fact that the way how neural networks work is still not well understood. So there is not a mathematical framework explaining how a deep network is working. So for us, it means we have to really develop custom models for our partners. And one of the main points here is the uncertainty we have to go into. So it's epistemic. On one hand, epistemic means systematic. So I do not have enough knowledge about something. And epistemic uncertainty I can reduce. And aleatoric, which is a statistical uncertainty, I can reduce. It's not reducible. So aleatoric means, as you can see in the name, alea, dice rolling is the prototype for this, and the epistemic is we just do not have enough data, for instance, or we have just low quality data, or I have too much variation in the data I have. So this leads to model uncertainty, and we have to address these points. So I will guide you a little bit through some examples how we are addressing these problems. So it's about some papers we wrote over the past 3 years. It's on reducing task uncertainty, reliability, and through data, model adaptation, and increasing controls through explanations. We already heard a lot about explainability in the past talks, and then model reliability in the more technical sense. So task uncertainty is something I wanted to bring that in because it starts with the question to the data. And this is an example, just very simple. Sounds simple, is not. Co-registering of follow-up studies of X-ray data. And you see here moving and fixed images, left and right, of the same patients. And what is done by our colleagues in all publications we found actually is that many optimize their AI-based registration to the lung field, which is partially misleading to the interpretation of the difference image, because the medical doctors want to see very specific parts, and it should be in a way agnostic to the disease. And what we found out is that it's very important that the restriction is not on the lung field, but on the ribs. And this led to much more informative difference images, which was done in a quite complicated way, because it was also done with a very limited amount of rib annotated data. So that was the whole process, working with a minimum amount of data and coming to the best possible outcome and to a very stable solution. This was done with Agfa Healthcare. So can we achieve more reliable analytics at lower imaging costs? It's also something, because if you image with lower resolution, it's less costly. and it's faster. Sometimes, in this case, we talk about satellite data. This is done with the Austrian, with the AMA. It's the regulatory agriculture. It's the regulatory body which is supervising agriculture areas in Austria. And actually, they had just Sentinel-2 data, which is low resolution, but with a lot of channels. And they wanted to learn how to super resolve these data to be able to segment reliably the very small plots in the Austrian landscape, and also to classify what is growing there. Yeah, so we had data pairs, low resolution from Sentinel-2 satellite data, and we had a couple of planet data sets, but not all channels were covered here. And at the end, we came up with a solution which was quite heavy, difficult to train actually, because we had to also fill in, we had like uncalibrated pairs, and we had also to learn the missing information. Another type of uncertainty is the model reliability. So I'm sorry, that seems to be due to the conversion again. So yeah, can we exploit multimodal information to outperform end-to-end trained single modality solutions? So can we include here more data into one model to get better segmentation in this case? Yeah, so and also we have done some work here, and we could show that we could achieve better segmentation on all channels, actually using all channels together, instead of really having even end-to-end trained segmentation models on a single modality. So the result was much more stable and much better than the other versions, which also means multimodality is doing it. If you have it, you should do it in a combined manner. Then also another question of reliability is how can we keep models updated? And we heard about the problem of catastrophic forgetting. So if I deploy Agfa Healthcare, for instance, is deploying their models all over the world. It's an international company. It has to work in every clinic. And the big question is, how can we keep models updated? And this is ongoing work, actually, and I'm sorry for the, my team is a fan of Homer. So, and yeah, so they came up with an idea, which is very, very efficient. It's about memory-based model, which can learn constantly new data. And it's an idea which exists for classification tasks, but here we further develop this for dense prediction tasks, which means image segmentation. And they developed a hierarchical memory, with quite sophisticated search mechanisms and update mechanisms, because the memory should also not grow too big. And this is just, it's on archive. It's currently under submission. And it's quite efficient because it has the same performance like existing models. And then another, yeah, so, and it also works on medical data, not only on Homer and March. So what else? Increasing control through explanations is, can we provide meaningful and reliable explanations to classifier decisions? That's also something which came up already. So GradCam actually is quite discussed as a not reliable solution. There is another possibility to do, and this is why by marginalization, so I exchange parts of the image and I look if the classifier is changing. But also here we see in the left down that this is also something which is critical to see, if you do not include domain knowledge, because if you just blur out a part of the image to find those regions which contribute to the decision, you get out of distribution because you change the data, you change the input data in a way which is not allowed, because the classifier would still deliver a result, but not necessarily from out of distribution data. And we came up with a solution which is actually overcoming this problem, which is taking domain knowledge, because we do the replacement of regions in a way that we fill it up with data which was trained, for instance, in this classification task for mammography, which was trained on healthy data only. So we make out of a diseased image a healthy image, and then we get a really reliable feedback on what we do, on how the classifier decides. Another thing is complex decision-making tasks. So here it's again mammography, it's very complex imaging data. And we said, okay, I mean, a diagnostic task is the breast dense, is there a tumor, is there, or a pathology, are there microcalcifications, are the microcalcifications malignant or not, or do they have a specific shape which is pointing to malignancy? And actually here we followed another strategy. It was a fusion strategy, saying, okay, instead of training end-to-end, saying, okay, is this diseased or not? Asking the questions, are there these specific steps and sub-results which are, we're then delivering similar results or as good performing results as the end-to-end solution, and also the, and keeping the transparency on the sub-decisions at the same time. The reliable outputs, actually state-of-the-art in anomaly detection, and this is then my probably last slide I will talk about. Here we are now on the level of the networks, and the question is, how can we deliver real probabilities as an output? Because a classical neural network is not delivering a real probability. It's a point approximation of the probability. And there are different strategies to achieve that. Many of them are very computationally expensive. They cannot be used in a practical setting. And so we have here on one hand some product networks as one solution, which deliver me then a full estimate and a density distribution of my latent space. And actually it outperforms everything else. So if I have a prediction task here, I can really get probabilities, the highlighted regions, which point me very, very clearly on the pathology. And the very last one, okay, I stop here. This is another possibility to do that. This is using energy-based models. This is something we currently work on. It's not yet published, so I anyhow cannot say too much about it, but it's a very elegant solution, and I can just recommend read into that. There are other publications which are using that, and this is highly efficient. So the importance of knowing what we don't know, this is actually my closing remark. This is a citation from Jaringal, who wrote that in his thesis. Yeah. Okay, thank you.